So there's the two problems. I have them worked here. Let me enlarge that some.
I think it's frozen. Yeah.
Oh, it's still frozen. There we go. Okay. All right, so you should have about 3.5 years on the first one. And about 6 minutes on the second one. And really the whole reason I wanted to look at these is I know when we were solving these last class, we didn't simplify the whole equation. All we did was kind of reduce. But in this one, I did simplify because I wanted to point out here, when you take that, again, we started with 36,000 and then we halved it to 18,000. If you do simplify it, what do you end up with on the left-hand side? A 1/2, okay? It's going to halve. So if we started with 50,000 and we said we were going to half it, it would be 25,000. When you go to simplify it, what's going to happen still? You're still going to get 1/2. So is it important to have an initial amount if you are going to take some amount and just cut it in half? You don't have to have an initial amount, okay? Same thing with number 2, except we were doubling on this one. Okay. And again, I didn't give you an initial amount on the doubling, but again, you don't need one, all right? So any of the problems that have doubling, quadrupling, halving, reduced by 4, okay? You don't need the initial amounts. You can just plug in the amount that the factor that you're trying to reduce or increase by. So that was the only reason I wanted to do these with you guys. Okay, any questions? All right, so then today we will jump into the lesson. We are solving exponential equations, and then we will be looking at the number E. All right. So in exponential equations, what's happening is that we've got some numerical value that serves as a base, and it's being raised to an exponent, right? So in this very basic example here, we've got a base of a. And again, the base can't be 1, right? Because if you have 1 as a base, it's always going to be 1 no matter what you raise it to. Right? But again, we have a base of a on each of them, and they have separate 2 different exponents, okay? However, if those 2 are going to be equal to each other, the only way to be equal is if the exponent terms are also equal to each other. So again, the bases have to be the same, and as long as the bases are the same, the exponent terms will be equal. So I'm going to run through 8 examples with you guys, and that's because they all have just a slight little nuance to them, just so that we see them, and then we'll talk about the number E, and we should have time to get started on the not homework, because what is this weekend? It's a no homework break, so we'll call it classwork, and we'll just kind of get through as much as we can today. And then what we don't get through, we'll finish up next time. Okay, are we ready to start the first one?
Yes.
All right. So we have 6 raised to the 5x plus 3 is equal to 6 raised to the x minus 9. So this one is nice in the fact that the bases are already the same for us. There's a base of 6 on each side, which means the exponents must be equal. So I'm just going to take that 5x plus 3 that's on the left and set it equal to the x minus 9 on the right. And now do we have a nice easy equation we know how to solve? Yes. All right, subtract the 1x from both sides. I'll get 4x on the left. Subtract the 3 from both sides. I get negative 12 over here. divide both sides by 4, and x is equal to negative 3. All right, these are usually pretty quick to check. All right, so again, if I just do a quick check here, this would be 6 raised to the 5 times negative 3 is negative 15 plus 3 would be negative 12 equals 6 to the negative 3 minus 9 is negative 12, and those two are indeed equal to each other. So x does equal 3, or sorry, negative 3. Yes, Emily.
So does that mean there are going to be extraneous solutions?
Possibly.
Okay.
Yeah. Okay, so on the next one, we have 3 raised to the x plus 1 is equal to 81. All right, so I need to figure out what that x is equal to, but my bases are not the same. However, can 81 be expressed with a base of 3?
Yes.
Yeah, what is it the same as?
3 cubed.
Is it 3 cubed?
3 to the 4th.
3 to the 4th, exactly. So I'm just going to re-express it. So on my left, I'll still have 3 to the x plus 1, but on the right, 81 can be re-expressed as 3 to the 4th. Right. So again, my bases are now the same. They're both 3, so I can set the exponents equal to each other. X plus 1 is equal to 4, which means x is equal to 3. And again, if I do a quick check, I'll get 3 raised to the 4th power, and is that equal to 81? Yes. Okay, so we have our solution there. Any questions so far? Are we ready for the next one? Yeah, okay. So the next one, I've got 5 raised to the 3x minus 1 is equal to 25 raised to the 2x. All right, so again, the bases currently do not match. However, can that 25 be restated? Yes. That's 5 squared. Okay, so my left side already has a base of 5, so it's not going to change. 5 to the 3x minus 1 equal to 25. I'm going to restate as 5 squared. But remember, all of that is still being raised to the 2x power. Okay, and what does it mean? What's the rule when we raise a power to a power? You multiply them. Okay, so that means, again, the left side is still 5 to the 3x minus 1. The right side is going to become 5 to the 4x. And again, my bases are now the same, so I can set the exponents equal to one another. So 3x minus 1 is equal to 4x. Subtracting the 3x from both sides, I will get negative 1 is equal to x. And again, I'm going to just do a quick check here. This would be 5 to the 3 times negative 1 is negative 1 minus 1 is negative 2. And is that equal to, if I take 25 raised to the negative, well, I did something wrong, didn't I? Negative 3 minus 1 is what? Not negative 2. Negative 4. Thank you. Okay. So again, we would have 5 to the negative 4 on that side. 25 restated would be 5 squared to the negative 2. And so again, those come out the same. So we are equal there. Any questions so far? Okay, so in D, I've got 9 to the x plus 1 equals 27 to the x minus 1. What's different in this one?
So simplified.
Not simplified.
Yeah.
Okay.
You have to change both of them.
Okay, both of them. 27 cannot be expressed as a power of 9, so that does mean changing both. What is the common base they both have? Both have 3. So we have to do it to both sides on this one. So 9 we will restate as 3 squared being raised to the x plus 1 equal to 27 we will restate as 3 cubed to the x minus 1. Okay. So one more piece we have to be careful with here is, again, the power to power rule means to multiply, but x plus 1 is a quantity, so what do we have to do? We have to distribute. Okay, so be careful with that. So the left side will become 3 to the 2x plus 2 is equal to 3 to the 3x minus 3. All right, so again, my bases are the same. I'll set the exponents equal to each other. 2x plus 2 is equal to 3x minus 3. Subtract the 2x from both sides. I'll get an x over there. Add the 3 to both sides, and I get a 5. All right, and again, I'm just going to do a quick check. This would be 9 raised to the 5 plus 1 is 6 is equal to 27 raised to the 5 minus 1 is 4. Okay. So again, putting this in terms that we can compare to, this would be 3 squared to the 6th, so that's 3 to the 12th. This would be 3 cubed to the 4th, so again, 3 to the 12th. So this indeed works. X is equal to 5. How are we doing so far? Okay. Do you guys find these easier than those rational expressions and equations? Okay. Ooh, what changed in E? There's a fraction. Okay. So the nice thing is, we already know what happens if we say, if we did like a to the negative 1. What is a to the negative 1?
1 over A.
1 over a. So that means we can go the other way around as well. What can we restate 1 over 3 as? 3 to the negative 1. So we'll change this to 3 to the negative 1. Again, all of that's being raised to the x minus 1. Equal to, and what will we restate that 27 as? 3 to the 3rd. Okay, so again, be careful because we're doing the power to power rule, and this x minus 1 is a quantity. So the left side will become 3 to the negative x plus 1 equal to 3 to the 3rd. And now I can set the exponents equal to each other. Negative x plus 1 equals 3. And I'm going to add the x to the other side and subtract the 3. So x equals negative 2. Again, just a quick check. If I do 1/3 raised to the negative 2 minus 1 is negative 3, would that be equal to 27?
Yes.
Yes. All right, remember this is the same thing as 1 over 3 to the negative 3. All right. Okay. We've got the same situation in F. Right, I've got that 1/2. So what can I restate the 1/2 as? 2 to the negative 1. So we have 2 to the negative 1 being raised to the 3rd power. And 16 we will restate as 2 to the 4th. Oh, all to the x. Yes, after we multiply the terms. So yes, we get 2 to the negative 3 is equal to 2 to the 4x, which means negative 3 is equal to 4x. So what does x equal? Negative 3/4. Okay, so are our answers always going to be nice integer values? No, not necessarily. So again, quick check here. If I take 1/2, whoops, it's 1/2, and cube it, is that going to be the same thing as doing 16 to the negative 3/4? Right. What's 1/2 cubed? 1/8 equal to, all right, what's the 4th root of 16?
2.
Is 2, and that would be 2 to the negative 3. Are those two the same?
Yeah.
Yes. Get the same thing. Okay. All right, how are we doing so far? All right. Okay. So now we've got 49 squared is equal to 7 to the x squared. What changed here?
We have squared for x.
All right, there is an exponent on the exponent, okay? But the rules work exactly the same way, okay? I need a same base, so I'm going to restate my 49 as a 7 squared. And again, that 7 squared is being squared, raised to the 7x squared. Okay, so power to power rule says 7 to the 4th is equal to 7 to the x squared. Now my bases are exactly the same, so I can set my exponents equal to each other. 4 is equal to x squared, which means what is x going to equal? Plus or minus 2. Okay. And again, just going to do a quick check. 49 squared equal to 7 to the, if I do negative 2 squared, I'm going to get what? Well, it's negative 2, all of it squared. What happens to the, it's going to become 4, 7 to the 4th power. Okay, is 49 squared the same as 7 to the 4th?
Yes.
Yes. Okay, and again, if I plug in the positive 2 squared, then what happens? Same thing. So we get 2 answers here. X can be positive or negative 2. Yes?
For some of the problems we've done in the past, if it already has the x squared, we have it where it only equals the positive 1. Why does this equal the positive and the negative 2?
Okay, because when you are plugging into the original, it can take both.
Okay, but like a few units ago, we were doing with like x that were like to the cubes and stuff. If it already had those, you said that it could only be positive.
Oh, so the cubes, yeah, because the cubes are odd. So if you take the cube root of, say, 8, it has to be positive 2.
Okay.
Right, versus, because it's going to be 2 times 2 times 2. That's the only way to get a positive 8. But if you had negative 8, it would be negative 2, because that would have to come from negative 2 times negative 2 times negative 2.
Okay.
So those are with the odd ones. But the even ones, anytime you're solving for the x and you're starting with an x squared, you have to consider both the positive and the negative. Okay. All right. So here is our last exponential. All right. So what are our thoughts?
You have to get 81 to 9 squared.
Okay, we're going to change that 81 to a 9 squared. So 9 squared raised to the x power is 9 to the x squared minus 3. Okay, power to power, so this becomes 9 raised to the 2x is equal to 9 raised to the x squared minus 3. Bases are now the same, so I can set the two exponents equal to each other. So we get 2x is equal to x squared minus 3. What did we just get? A quadratic polynomial.
Oh,
more specific. Okay, which means what are we going to have to do to solve this one? Set it equal to 0 and factor. Exactly. So we end up with x squared minus 2x minus 3 equals 0. What does this factor into?
X minus 1. X minus 1.
Yay! X minus 3, x plus 1 equals 0. Therefore, x is equal to negative 1 and 3. All right, so again, I'm going to do a quick check over here. So I have 81 cubed, and again, is that equal to, if we do 9 raised to the 3 squared would be 9 minus 3 is 6. Okay, again, 81 can be restated as 9 squared, which would be 9 to the 6 equals 9 to the 6. So that one does work. And if we try the negative one, 81 to the negative 1 is equal to 9 raised to negative 1 squared becomes positive 1. Positive 1 minus 3 is negative 2. Are those going to be the same? Yes. So we have two solutions in this one. All right. So any questions on what we've done? Okay. So what we're going to look at next is the number e. So we're going to start with an exploration. You're going to want your calculator for this. We talked about compounding interest last class. Anybody remember what that formula is?
It's y equals
P times 1 plus r over n whole 10 power n t.
Okay. All right. So that was our formula for compounding interest. Okay. So what I want you to now do is we're going to say that we're starting with an investment of $1, which would represent what in our equation? That's the P. And we're going to do an annual interest rate of 1%. 100%. It's only 1 year. And again, it's annual, so we're only compounding one time, which means what does n equal to? 1. Okay. I'll let you guys calculate that and tell me how much money we have after 1 year. Did you get something? How much? $2. Okay. So after 1 year, if we only compound one time, we get $2. Okay, well, let's say we're going to take that same amount of money, the same principal, same interest rate, but now we're going to compound semi-annual. What does that make n?
2.
Okay. So now n is equal to 2. I'll let you guys calculate that again and tell me how much money that is. What's that? It's not 4. $2.25. Okay. So again, same amount of money, same amount of time, same interest rate. What's the only thing that changed? Yeah, the number of times we compounded. Okay. We can do the same thing except monthly now. What does that make n?
12.
That makes n 12. All right, I'll let you guys calculate that. What'd you get?
6.6.
$2.61. Is that it? Okay. So what's happening? Okay. The more times we compound, okay, we're making more money. Okay. Well, what if I now ask you to compound weekly? What does that make N?
52.
Okay.
2.69.
$2.69. So now what happened? But by a smaller amount. Okay, what if we said let's compound daily? Now what would that make N?
2.71.
So N would be 365, and now we would be at $2.71. What if we went to twice daily? That's an N of what, 730? Anybody calculate that already? Let's go ahead and go 3 decimal places.
2.716.
Okay. 2.716. Now what's happening?
It's not really growing.
Not really growing very much. Anybody want to try by the minute?
By the second.
By the second? I don't know how many seconds there are in a year.
How many minutes are here?
I only know that by the song. No, nobody knows.
525.
Oh my gosh.
There you go.
I thought it was just saying a random number.
No, it's from Rent.
Oh, times 60. Do that
Huh?
times 60. And then you'll get the number
Uh-huh.
of seconds.
Yes. Yeah. It's gonna.
31,500,000.
Okay, so the next one you got was 2.718. What other decimal places do you have?
2.718279244.
279. 244. Okay, we'll stop there because this goes on. Okay, so what's happening is we are approaching this lovely number, which we call E.
Oh.
Oh, that's crazy.
Okay.
Well, I'm these seconds right now. Can we do any number? Like it does.
Huh? Well, so remember, it's as n gets larger and larger and larger and larger. So, what n did you use on your last calculation?
525.
Okay, yeah. So that was because that was by the minute, right? And Mira, did you ever plug in the one to the seconds every?
Yeah, I got 1.00031, but I think I did something
Okay.
for sure. So
Okay.
let me
All
just-
right. So the number E, it's an irrational number. What does it mean to be an irrational number? Doesn't stop, and also doesn't have any repeating patterns, right? Who's our other famous irrational number? Pi. Yeah, so it's like pi. Okay, so what's happening here is as x grows, if you take 1 plus 1 over x and raise it to the x power, you will, and take x to infinity, so x is getting infinitely larger, it is eventually going to even out to the letter E that we call. Okay, so because if you think about it, what happens if you take 1 divided by a super big number? What is it going to get close to?
0.
It's going to get close to 0, right? So eventually, when x starts getting so large, it's almost like adding 1 plus 0 at the end and then raising it to a power, right? So it eventually will even out to E. Okay, so as we saw, the more times we compounded, we were making more money, but eventually it started to slow down. Yes.
I got the number for seconds. It's 2.7182824.
Oh, you see how much closer you got?
Yeah.
Yep. Got even closer. Okay, so we do have a way to calculate when we compound continuously. All right, so When we're compounding continuously, we're not talking about like every second. We're talking about like every millisecond. It's constantly compounding. And so that formula is A equals P times E raised to the RT. All right. The parts of this formula are the same as the other one. So again, A, that's the amount that you will have after T is still years. What does the P represent?
The principal.
Principal, or the initial amount that you start with, so that doesn't change. And R represents the rate of interest. So that part doesn't change either. Honestly, this is a much easier formula to work with, yes?
Yeah.
Yeah, it doesn't have that fraction in there that you have to simplify and all. And I usually just call this the PERT formula. PERT. Okay. Oh, did I pass out the... Okay. So these are the next two examples. They're printed for you so you don't have to write them all down. So we've got $20,000 to invest at 4.5% interest rate compounded continuously. And the question is, how much money will we have after 3 years?
Thank you.
All right. Okay, so that $20,000 is what? That's our P. So we have P is equal to $20,000. Okay, that 4.5% interest rate is our rate, and we will convert it to 0.045. And we are looking at the end of T equals 3 years. All right, and so we'll just plug that in to our PERT formula. A is equal to 20,000 times E raised to the 0.045 times 3. Okay, so I know that when we are working with pi, we often round it to 3.14. Don't want to do that here, so let me show you where. Let me clear all this. Okay, so we'll plug everything in. We've got the 20,000 times. Now the E button is located above this natural log, so you'll have to hit second natural log, and then you'll see it's always going to give you E raised to whatever you want to raise it to. Okay, if you're just wanting to do E, what will you plug in? 1. Okay. In this case, though, we want to plug in 0.045 times 3, and then we just hit enter and let our calculator do the work. Okay. And since this is a money question, we'll go ahead and round to 2 decimal places. So A is equal to, was it 22,890 and what, 74 cents?
Yeah.
Is that right? Okay. All right. That's not too bad. That means you made how much money?
2,000.
Yeah, close to $3,000 just for letting it sit there. Okay, one last example. All right, so you and your friend each have accounts that earn annual interest compounded continuously. The balance A in dollars of your account after T years can be modeled by A is equal to 4,500 times e to the 0.04t. The graph shows the balance of your friend's account over time. Okay, so I'm going to put over here that this is our friend. Okay. The first question is, which account has a greater principal? So again, what does principal represent? The initial amount, okay? So if we're looking at, I'll just call it our account, what is the principal in our account? 4,500. Okay, and that is equal to P. Okay, but now I want to look at our friend's account. How do we determine the principal in our friend's account? The y-intercept, and the y-intercept is at $4,000. $4,000 equals P, and again, yes, it is the y-intercept. So at time 0, they had $4,000. Okay, the next question is, which has a greater balance after 10 years? Okay, so what are we going to have to do regarding our account? We're going to have to plug in. So for our account, we will do A is equal to 4,500 times E raised to 0.04 times 10. Anybody calculate that already?
Yes.
Yep, what'd you get?
6,713.
$6,713. Okay. And so what are we going to do with regards to our friend's account?
Find it on the graph.
Find it on the graph, and we're going to look for t equals 10, which is here, and look to see where our graph is at t equals 10. And what do we see there? It's just over 7,000. So our friend has just over $7,000. Okay. So therefore, our friend has more money. Okay, so if we started out with more money and our friend ended up with more money in 10 years, what does that mean?
Their rate is higher.
Yes, so our friend had a better interest rate. All right. Any questions? Okay, so there are some bookwork problems that this is really all about E. It's just simplifying and working with E. And then I have a worksheet for you, and we will just do as much as we can today.